So this video is about how we manage to use L'Hopital's rule for the multiplication indeterminate form. And I shouldn't even say forms because as far as we're concerned there's only one indeterminate form, and that one indeterminate form is 0 times infinity. Right? So I hope we're all convinced that 0 times infinity really is an indeterminate form. If you're not, be sure to write down your question and ask me about it during class. It's a valuable thing to talk about. So the good news is L'Hopital's rule can be used. It can be used for 0 times infinity. Well, we can make it work, right? What we have to do is we have to find a way to write this thing in one of these two forms. If I can find a way to rewrite it in terms of 0 over 0, infinity over infinity, we automatically win, right? And so here's how we're going to do it. I'm going to sort of give you the general overview here, and then we'll get to some examples. Suppose that this first function is called f of x, and the second function is called g of x, right? This one's approaching 0, this one's approaching infinity. What we can do is we can pick either one you want. For my purposes, I'm going to pick this one. You can take this one, and I'm going to write something kind of weird here. F of x is equal to 1 over f of x. I don't know if you recognize that, but basically what I'm saying is if you take the reciprocal and then its reciprocal, you get back the original function. The other way of thinking about this is if you were to multiply top and bottom by f, it would cancel in the bottom and leave you with just f on top. So what that means is I can take this expression here and rewrite it as g of x over 1 over f of x. And the reason that's neat is, remember, what is g of x approaching? G of x is approaching infinity. And what's f of x approaching? Well, f of x is approaching 0, but that means 1 over 0 approaches infinity. And we've taken our expression and written it as infinity over infinity, right? We could also just as easily, let me scoot sideways, we could just as easily have taken this thing and written it as f of x over 1 over g of x. So our strategy for these problems is basically going to be, if you have two things multiplied together, instead of multiplying, divide one of them by the reciprocal. And then you'll have an indeterminate form. You'll have something that's 0 over 0 or infinity over infinity, and you'll be able to use L'Hopital's rule. So I've got 3 examples. Let's take a look at them. Here's the first one. I want us to evaluate this limit. The first thing we do is we attempt to plug in infinity. We may not even have an indeterminate form. Probably not, but we'll try. If we attempt to plug in a very large, if we attempt to evaluate the expression for infinity, I end up with infinity times the sine of 1 over infinity, which is basically 0. This is infinity times 0. Okay, so we do have an indeterminate form. What I'm going to do is I'm going to rewrite this thing. I'm going to pick either this or this to write as a reciprocal in the denominator. Now, which one is significantly easier to write? I really hope you guys recognized it was this one. It's much easier for me to write the limit as x approaches infinity of the sine of 1 over x over 1 over x. In theory I could have done x over 1 over the sine of 1 over x, but that's just a mess. Especially because what's your next step? Your next step is, hey, look everybody, this is approaching 0 over 0, so I can use L'Hopital's rule. I can do these two derivatives. I would much rather do these two derivatives than these two derivatives. So let's just, I can't make that go away. Oh well. We'll just sort of scratch it out. Working through this problem on the left, I want to do L'Hopital's rule here. In fact, I'd like you guys to do L'Hopital's rule. So now that this is set up for L'Hopital's rule, you take the derivative of the top and the bottom, see what you get. What we end up with is the cosine of 1 over x times chain rule times the derivative of what's inside, that's negative x to the negative 2, over the derivative of 1 over x, that's also negative x to the negative 2, which is like marvelously convenient because it means these two things divide to be 1. And all I'm left with is this limit as x approaches infinity of the cosine of 1 over x. And so how do I do that? Well, I attempt to evaluate this for infinity. When I plug in an incredibly large number here, the inside of this is turning into the cosine of 0. And what is the cosine of 0? Cosine of 0 is 1. So this limit, this 0 times infinity indeterminate form, turns out to actually be 1. Sometimes it'll be 1, sometimes 0, sometimes infinity, sometimes it can be anything, right? Great, let's move on to the next one. So here we have the limit as x approaches infinity of x times e to the negative x. I'd like you to pause the video and try this one on your own. See whether or not you can recognize it as indeterminate, then change the form, and then do L'Hopital's rule. So first of all, is this really indeterminate? As x approaches infinity, I have infinity times e to the negative infinity. That means like 1 over e to the infinity, which is like 0. And so I'm getting infinity times 0. Sure enough, this is my multiplication indeterminate form. It means I need to transform to get this to be L'Hopital's rule. Again, I can sort of choose either one of these things, or in this case, it's actually really neat. We could just do the limit as x approaches infinity. We could just rewrite it as x over e to the x. That's a really nice, easy way to rewrite this thing. And when I do, this approaches infinity over infinity, which means we can use L'Hopital's rule, right? So again, I assume that you've already tried using L'Hopital's rule. If you haven't, pause and try again. Or rather, try, not try again. Limit as x approaches infinity, we'll have 1 over e to the x. I just did the derivative of x and the derivative of e to the x. Now as x approaches infinity, the top is 1, the bottom is ridiculously large, and that's not indeterminate at all. This is clearly approaching 0. So this time, my infinity times 0 gave me 0. Right? It was 1 in the previous example, it was 0 in this one. We'll see what it is in the next one. So here we have the limit as x approaches 0 from the right of x times natural log x. When we attempt to evaluate for 0, we get 0 times negative infinity. Some of you may not, and I'm still worried about that. Remember natural log x looks like this? Like that's effectively what natural log x looks like. It has a vertical asymptote here at 0. That vertical asymptote means that as I approach 0 from the right, this is approaching negative infinity. Right? So again, we need to transform this to use L'Hopital's rule, so I hope you'll try that on your own. I'm going to have the limit as x approaches 0 from the right of, I'm going to do it as natural log x, not ln x, but just ln x, over 1 over x. This is approaching negative infinity over infinity. Some people worry about whether that's L'Hopital's rule. It absolutely is. Having a negative in there doesn't matter. It's not a big deal. So L'Hopital's rule says that I can take the derivative of the top and the bottom. That gives me 1 over x over negative 1 over x squared. And now this thing is interesting. If we try and plug in 0, we get infinity over infinity. If you keep trying to do L'Hopital's rule, you're just going to get more and more larger and larger negative powers here. What I'm going to do instead is I'm going to multiply top and bottom by x squared. So as you can see, L'Hopital's rule isn't just like a magical fix-everything kind of thing. It's a marvelous tool, but sometimes we still need our knowledge of algebra and analysis to do things. I now have the limit as x approaches 0 from the right of x over negative 1. And now as I attempt to evaluate for 0, this is clearly approaching 0. So this one turns out was 0 as well. So we had two problems that were 0, one that was 1. They literally can be anything. As you'll see in the next example, they can be a lot of different things. So I'll see you in the next example for more awesome problems.